The Standard Normal Distribution, Module 4, Part 2. Our objectives are to find the area under the standard normal curve, find the z-scores for a given area, interpret the area under the standard normal curve as a probability. Standard normal just means we have standardized the data with z-scores so that the mean is 0 and the z-score tells us how many standard deviations the data of interest are from the mean. The empirical rule gives us a way to estimate the area under the curve for whole number standard deviations from the mean. By standardizing the data, we can look up the area under the curve for any decimal z-score with technology or by using a table. The properties of the normal density curve. First, it is symmetric about its mean, mu equals 0, and has a standard deviation of 1. The mean is equal to the median and it's equal to the mode, and they all equal 0. Its highest point occurs at z equals 0, the single peak in the graph. It has inflection points 1 standard deviation above the mean, which would be a z of 1, and 1 standard deviation below the mean, a z-score of -1. The area under the curve is 1. The area under the curve to the right of the mean equals the area under the curve to the left of the mean, both of those being 1/2. The far left and right tails of the curve get close to the horizontal axis, but they never touch it. The empirical rule that we studied in Module 2 applies. Note that these are the same properties as before, but we are using the standard scores where 0 is the mean, but the shape of the normal curve is exactly the same. And this should be getting familiar to you at this point. The top is the standard normal curve with percentages, and the bottom graph has decimals instead of percents. So let's look at finding the area under the standard normal curve. This is a website that you can use to calculate areas for particular z-scores. It gets updated from time to time, so the screenshots in this presentation may not look exactly like the website, but it should still function the same. If not, please let me know. Find the area under the standard normal curve to the left of a z value of -0.38. Note to the left of -0.38 would be the numbers that are smaller or below -0.38, which is the terminology that the website uses. It uses below instead of left. Keep in mind that this is the same thing we did in the last lesson, only we used the empirical rule to estimate area because we had whole number standard deviations. The areas that were given to you in the problems that ask you to interpret areas were generated with software or read from a table, those decimal values. Find the area under the standard normal curve to the left of z equals -0.38. So to use the website, you'll have your mean of 0 and your standard deviation of 1, and we want below, so we'll put our -0.38 in there, and it will calculate the area to be 0.351973, which you can round to the number of decimal places needed. And I'm skipping the TI-84 slides. Now find the area under the standard normal curve to the right of a z of 1.25. Stop and see if you can calculate this before you go to the next slide. So here we want above, so we would put our 1.25 into the above section, and we get a shaded area of 0.105650. And notice the website shades the area so you can see if it's calculating what you want it to. Find the area under the standard normal curve between z equals -1.02 and 2.94. So this is a between problem. Stop and see if you can work it. So we use the between section on the website. Type in our -1.02 and 2.94, and it tells us that the shaded area, which it shows us, is 0.844495. So the area between -1.02 and 2.94 would be 0.8445. Now let's find the z-scores for a given area. Now we reverse the process. If we know the area, can we go backwards and find the corresponding z-score? To do this on the website, choose the second option under the graph. Find the z-score such that the area to the left of the z-score is 0.7157. So they've given us area this time. So we type our area in, and then we click below, and it tells us that the z-score such that the area to the left of that z-score is 0.7157 would be a z of 0.57. Find the z-score such that the area to the right of the z-score is 0.3021. See if you can do this before you advance to the next slide. So we put in our area of 0.3021, click above, and it tells us that the approximate z-score that corresponds to an area of 0.6979 to the left, or 0.3021 to the right, is 0.52. Therefore, z is equal to 0.52. Find the z-scores that separate the middle 80% of the area under the normal curve from the 20% in the tails. So you would have 10% on each tail. Stop and see if you can use the website to figure this one out. So we would put our area in, and notice you have to change the 80% to a decimal, 0.8, and click between, and the z-scores are given to you. The middle 80% of the data would be between a z of negative 1.2816 and positive 1.2816. The notation, pronounced z sub alpha, is the z-score such that the area under the standard normal curve to the right of z sub alpha is alpha. So this is just mathematical notation to keep them from writing so much. Find the value of z sub 0.25. So you're finding the z-score such that the area is 0.25 to the right of that z-score. So you put 0.25 in as your area and click above, and you have 0.6745 as the z-score. Now let's interpret the area under the standard normal curve as a probability. A probability tells us the likelihood that something is going to occur, and this is just some notation using the less than and greater than signs. This is the probability that your z value is between A and B. This represents the probability a standard normal random variable is greater than, so you've got your greater than sign from algebra. And this symbol represents the probability a standard normal random variable is less than A. So here's a problem using this new notation, but we're working the same types of problems that we did before. So find each of the following probabilities, and remember probabilities are the same as area under the curve. So you're doing the same thing that was stated in words earlier. So A would be find the probability that you will get a z-score less than negative 0.23. So you're going to want the area under the curve to the left of negative 0.23. Stop and see if you can work these. So you want below, and you would put in negative 0.23 and let it calculate the area. Remember that you need to check the other option on the graph because we're back to calculating areas from z-scores. And the probability that a z is greater than 1.93, that area is going to be 0.026803. And the probability that you have a z between 0.65 and 2.10, use between, and the probability is the same as the area, so it's 0.239982. For any continuous random variable, the probability of observing a specific value of the random variable is 0. For example, for a standard normal random variable, the probability of A is equal to 0 for any value of A. This is because there's no area under the normal curve associated with a single value, so the probability must be 0. If you think about when we first started talking about area and we looked at a little rectangle, if you only have one value, you can't get any width to your rectangle. Therefore, the following probabilities are equivalent, and all this is saying is that it doesn't matter whether there is a bar under your less than or greater than symbols, you're going to get the same area either way. Now try these examples. Find the area of the shaded region in the following graphs. Stop the video and work these problems before looking at the answers on the following slides. So here the shaded area would be 0.019806, and we're using area outside our z values instead of between. Here we're using between. You put in your z values and find the area to be 0.368643. And again, we're using between, and find the area between negative 1.96 and positive 1.96 to be 0.950004. Now take Module 4, Part 2, Assessment of Learning. The password is standard in all lowercase.